Hey guys, welcome to the part two of the FMECA lecture. I'm going to be going first through the detailed process of the FMEA and the FMECA and kind of explaining some of the differences between those two as you go through that process. And then the second part of this lecture is going to be a couple of different examples. So we'll go ahead and get started with the process portion first. So first off, here's a detailed process diagram. This shows 10 different steps for completing either a FMEA or a FMECA. And I'll kind of explain again the differences between those two. But this process that's shown here fits very well with either methodology, and it also fits well to MIL Standard 1629. As I go through this, I'm not going to talk about every single step. There'll be a couple that I'll leave out. I think for completeness, I'm showing all 10 steps, but some of them I'm just going to go through in a little bit more detail. So I'm going to kind of be selective with the ones that I go through. So first step that I'm going to present to is determine potential failure modes, right? And this is one of the major steps, of course. It's a very clear feed into the analysis. And kind of the format that I'll be following in the next several slides to show you guys the process is going to be, I'll show some kind of examples within this as well, but a lot of what this kind of talks about is the responsibility. So given that you're in an organization that has a variety of different engineers, as you can kind of see here on this slide, reliability, hardware design, software design, safety, chief engineer, systems engineer, they all play a different role in the FMEA process. And so the way that these next couple of slides are laid out is they basically show you the individual that's responsible for doing a particular task and then also what that task is. So this works well with DoD style FMEA methodologies. So in this particular case, for determining the potential failure modes, there's a variety of different people that are involved. And of course, this does depend a little bit on where you are. But as kind of a standard, the reliability engineer is the overall person responsible for identifying these failure modes. And you'll find this done in a variety of ways. It may be using FMD 97, which we've previously talked about. That's Failure Modes Mechanisms Distribution 1997. And this was developed by the Reliability Information Analysis Center. And it essentially lists failure modes by component type. So if you have a pump, it'll list particular failure modes. If you have an electrical circuit or electrical component, it'll list failure modes by those particular components. So it's a very nice resource. It could also be that you find during testing, you find different failure modes, or potentially the supplier has failure modes as well. So there's different ways to find it, but the reliability engineer is the overall person responsible for going through, taking the system, and specifically identifying these. But it also mentions, for example, the hardware design engineer and the software design engineer are two other critical people. And the reason there is because the hardware and software design folks tend to be very involved in the system, and not just the system, but the very minute details of the system. And so they can be a critical factor in determining, all of the correct failure modes for the system. So they are very, very important. And the safety engineer, because of the way that they perform their assessments, they have a variety of hazard analyses, which in a lot of ways are very similar to a FMEA or a FMECA. And so they may also have some failure modes that should be included in the analysis. And so they're that's a good position to bring in when developing these. The output of this step then would be a list of failure modes, a total list, but it might be a list for the particular components, or maybe it's by function. But the goal at this step, of course, is to develop the entire list of failure modes. As I mentioned just a second ago, FMD 97 is a good potential source for determining this. On the right-hand side is a snippet. This isn't out of FMD 97, but it's very similar in that it lists essentially the component on the left side and the failure mode on the right side. And there are a variety of different resources out there Some are internal to organizations, and so your organization may have some of these. Some are a little bit more broadly available, like FMD 97, and some are more geared toward particular industries. So there's some in the automotive industry, and there are some in the nuclear power industry, and so on and so forth. So it's best to kind of follow the documents that are within your industry, because the failures tend to be a little different, but it can also be valuable to look outside your industry as well, depending on how complete the analysis is. Depending on the type of FMEA being done, it may be valuable to understand how to develop failure modes in the absence of having actual components of the system. So for example, let's say you're very early in the design process and the architecture is either not defined yet or is defined with a lot of uncertainty, meaning that what the system looks like and what the components are that are being used is in flux. And at that stage of design, hopefully there is some understanding of what the functions are. If you do have an idea of what the functions are and you still don't know what the actual components are, you can use this methodology that I'm presenting right here, which is to basically look at how functions fail. So there's about, I believe, 6 different ways that we can look at how functions fail. So I'll kind of briefly describe those, and we'll use the example of provide thrust for a rocket motor or a booster on a missile. So the first one is that the function occurs too early, right? And so the effect of this in this particular example would be a safety concern. You can imagine having a missile on an aircraft or on a carrier of some sort, and having it go off before it's supposed to. So that'd be, as an example, during captive carry or just during storage of the weapon, having it go off. So pretty obvious safety concerns there. The function occurs too late, so the effect of that would be a mission failure typically. And so that would be the case where, for example, the weapon was dropped from an aircraft and the booster didn't light, or the weapon was being launched from an aircraft and it didn't go off, so it just failed. So in that case, it wouldn't be a safety concern necessarily. It would more likely be a mission failure. Too much of the function is another way that functions can fail. In this case, it would likely affect the flight trajectory, but this is kind of an interesting example given the rocket motor, because the amount of thrust for the most part is determined by the burn rate and by the actual volume of the booster material. So in this case, it's very unlikely, it might not even be possible to have too much of the function. And so a better example of too much of the function might be related to providing power, right? So that would be like a surge, an overcurrent situation. A few more examples here. So not enough of the function is another way to look at it. This would relate in a mission failure as well. Most likely the flight trajectory wouldn't be able to be maintained. The function does not occur is kind of the obvious one, right? So if you look at the functional architecture of a system, you can easily go through and say, well, what happens if this function doesn't occur? So that's essentially what's being done here. And of course that means a mission failure, right? Because we designed functions to be relevant to the system. And so very few cases where a function can fail and it doesn't affect a mission. And then the only other scenario that you can really get out of this is an intermittent, which means that the function essentially is either working completely and then stops working and then starts working completely again, or it's some combination of degraded behavior as well. So it could be going from 100% working down to 50%, something like that, or it could be intermittent between partially working and not working at all. So that's another way to look at it. So essentially this slide and the previous slide are ways to look at how the functions of the system can fail if the components are not available. But I should also say that you can essentially provide this same sort of methodology to components. And that's because all the components have functionality assigned to them, in terms of how the system is supposed to work. So even if you do know the components, you can take this methodology and apply it to the components as a way to get more failure modes of interest. Especially in case where you have, let's say, a new portion of the design. So if you're designing a new weapon system and part of the system is reused, but part of it is fundamentally new design, and you want to focus your FMEA a little bit more on that new part of design because it's more uncertain, you may find some failure modes for the components there, but you may also use an approach like this to develop more failure modes. Okay, so the next step of the process is the failure modes and effects analysis portion, which is another major step. In terms of responsibilities, the reliability engineer defines the severity levels and categories and essentially provides those to the systems engineer, and the systems engineer determines the system level effects. Again, this is kind of what we might call the standard approach, but it is often true that the reliability engineer actually does both of these. But I would say that in the case where the reliability engineer does do both of these, it is important for them to work with the systems engineer, because systems engineers are particularly good about having a really good knowledge across the whole system. And well, that's ideal for the reliability engineer to know as well. The systems engineers often have a better knowledge of it. And so using the responsibilities provided here is a really good methodology, but if as a reliability engineer you decide to determine all the effects yourself, it's critical that instead the systems engineer does a really good review of those. And then so the output of this step is the severity, the effects and the severity. Step 5, identify possible failure mechanisms and causes. So this can be done in a variety of different ways. It involves quite a few people. So of course the reliability engineer is kind of the coordination of this activity. And again, depending on the style of the program, they may be actually the one performing all of this. But especially for bigger programs and where there's more people involved and the size of the system grows and there's a lot of complexity, the reliability engineer often has to lean on other individuals to actually accurately be able to do step 5. And so it brings in essentially all the other core engineers that are part of different elements of the system. So thermal, mechanical, electrical, components, materials, those types of engineers essentially are going to be the cornerstone of determining what those causes are. Now, I would say that you're likely not going to find a thermal engineer giving you the actual formal failure mechanisms of the particular failure mode that you're looking at. Most likely, they're going to discuss with you what the causes are of those failures, and you're going to have to understand what that means in terms of failure mechanisms, if that's the way that you list it on your FMEA. But these other types of engineers on the program will be really important for determining what those causes are, because they have such a detailed knowledge of their portions of the system, whether it be the mechanical portion or the software or the thermal side of it. So it's not a particular part of the system, but just an understanding of the heat transfer throughout the entire system. Okay, so the next step is to identify the detection method. One thing I'll say about this step is this is one of the things that segregates FMEAs from FMECAs, and that is that FMECAs list the detection method, so it's important to identify it for the FMECA and list it in the column. For FMEAs, the difference is that not only do you identify what the detection method is, but you give it a score on the scale of 1 to 10. So it actually gets wrapped into the risk quantification. So that's the primary difference between FMEAs and FMECAs. In terms of responsibilities, we don't formally list reliability engineer in this step, although again, it just really depends on how your program is run. It's true that this entire process, I've seen this done before where the reliability engineer does the entire thing. So it's important to keep that in mind. But the software design engineer and the testability engineer and the electrical and mechanical engineers are really important for this step. And that's because, again, their knowledge of the system is going to be more detailed than the reliability engineer. And so in terms of how, especially the test engineer and the software design engineer in this particular case are really important, because the software design engineers typically are the ones that are doing a lot of the controlling of sensors and understanding what sort of sensors are in the system and what information they're taking, when it's available, how it becomes available. And so they're going to be really critical. And the test engineers typically work with the software engineers to actually do that. And it's true that the electrical and mechanical engineers are part of that loop as well. But the software design engineers and the testability engineers are particularly useful for helping the reliability engineer understand what those detection methods are. Step 7 is what we're calling the criticality analysis here, but it's really the step in which we quantify the risk of all the failure modes. And this is the kind of the key step that segregates FMEAs and FMECAs. So I'll talk a little bit about each of them individually. The key difference in terms of quantifying risk between the two methods is that FMEAs use what's called an RPN, or a risk priority number, and FMECAs use a criticality analysis. And the criticality analysis can either be done qualitatively or quantitatively, which I'll mention here in just a second. To start with the FMEA side, talking about the RPN, this is something that was previously stated in the first part of this lecture, or the previous lecture. So the risk priority number is determined by 3 different individual values: the degree of severity, probability of occurrence, and the ability to detect. Okay, and you can see that in the probability of occurrence column, there are some numbers. Those are not the numbers that go in the spreadsheet. The numbers that go in the spreadsheet for each of these 3 columns are the 1 to 10 rating on the far left side. So for example, a particular failure mode could have a 1 for degree of severity, a 5 for probability of occurrence, and a 1 for ability to detect, which would indicate that there's very low severity. It happens fairly often, but it's very easy, and there's a high probability of detecting it when it does occur. So because the 1, 5, and 1, the combined RPN value, or the combined risk, would be a value of 5, because it's the product of the 3. Now in the probability of occurrence column, there's more of the qualitative type of assessment as well as the quantitative assessment, and this is also true for the ability to detect column. But with the probability of occurrence column, in the case of certain failure modes, there may not be the availability of data to be able to actually quantify what the probability is. And so someone like a SME might have to indicate, based on their experience, how often they've seen a particular failure mode. And so as a result, it becomes a little bit more qualitative in that case. But and you may go to the supplier for that as well, especially for failure modes of particular components. The supplier will often have the most data, especially for a very specific type of component. And also the supplier, especially on the data sheets that they provide when components are being selected, they will often have the actual failure rates, or even the probability of occurrence in some form or fashion. And if that information is available, the right side of the probability of occurrence column can be used. And then as a result, it can be more of a quantitative approach to determine the actual rating score. But again, with each failure mode, you'll determine what each value is and multiply those together, and that's the RPN for the particular failure mode. So in comparison, the FMECA criticality analysis is a little bit different. It's very similar in some ways. I guess First way is looking at the likelihood classification. So instead of a 1 to 10, it's A through E. So it's a slightly smaller scale where the probabilities are grouped together a little bit more. And you can see that this also supports the qualitative and the quantitative type of approach. So you can see here that, for example, category A is frequent or has a probability greater than 0.2. Right? So 1 out of 5 times in a mission, this failure would occur. So it's very, very frequent, right? So that's shown here. We can also look at the definition right here on the right side. So for the category A, this is a high probability of occurrence during the item operating time interval. High probability may be defined as a single failure mode probability greater than 20% or 0.2 of the overall probability of failure during the item operating time interval. Right? And so, again, for each failure mode, and this is in lieu of doing the FMEA style, right? Because you're only going to quantify the risk if you're doing a FMEA, you're going to be using RPN values. If you're doing a FMECA, you're going to be choosing for each failure mode, you're going to be choosing one of these categories. So that's the first step for the criticality analysis. And the second step is to determine the severity classification. And so there's 5 different categories, again, just like the probability of occurrence. And they range from catastrophic all the way down to negligible. And just as before, they've got the definitions to give you some understanding of what the actual classification is. Now, it is important to keep in mind, especially in the DoD world, and especially as a higher up integrator of a system, that when you go into a program and define the way that a FMECA or a FMEA is going to be done, that the information that you put into your reliability program plan on the way it's going to be done includes how you're going to flow it to suppliers. The reason that's important is one of the things that this definition right here doesn't show for the severity is what the cost related to a particular failure is. And if you think about the way that systems are designed and the way that the supply chain works, there will be some suppliers that say a $10,000 loss is going to be catastrophic. And that might be related to the size of that company. It may be related to the cost of their particular part. And so a $10,000 failure might be catastrophic for one company, but for another company or supplier, it may be $1 million is catastrophic. So while these definitions here don't provide any dollar amounts, a lot of times particular organizations will actually put in the dollar amount that they consider to be catastrophic, and they force the supply chain to kind of adhere to those definitions. And I think that that's a good approach. I've seen it work really well before, and so it's something you might consider following. What you're seeing here on this slide is a fever chart which displays the probability of occurrence on one axis and the severity on another. So this is the combination of the previous 2 slides. For a particular failure mode, you would determine, again, the likelihood and the severity, and that would determine where that failure mode falls on this chart. Okay, so the chart on the bottom here shows, again, the severity versus the likelihood, and it has been determined that certain combinations of severity and likelihood relate to certain risks. So instead of having a more detailed value for the risk as you would in an RPN, this is presenting it in a slightly more binned way. So for example, if a failure mode's severity is negligible, regardless of what the probability is, the risk level is low, right? And that's what you see by the green on the kind of the far left side of the color. And if it's catastrophic, if the severity is catastrophic, it is almost certainly going to be either high or serious risk. The only exception to that is if the likelihood is extremely unlikely, then it'll be a moderate level of risk. So it's pretty obvious that catastrophic failure modes, no matter what their probability is, are very, very important, right? And then another thing about this chart, when actually developing the FMECA analysis, it's good to show an image exactly like this in the section where you describe your methodology, so how you're going to execute the FMECA, to show essentially the image here with the different risk categories in it. Now, it's very traditional in the actual analysis portion of that document to show this exact same chart again, but instead of having the numbers and letters in the boxes, the 5A and 5B and the 4A and 4B and so on and so forth, to show actually the number of occurrences that are in those boxes, right? And so, for example, instead of having 5A here, it may be that there are 200 of those particular failure modes, the negligible and frequent. And so in that box, you could list 200. And the reason that that's important is it gives somebody at a really quick glance a really nice overview of what the total risk is, right? And you could, of course, add up all the greens and the yellows and oranges and red and present it that way as well. But just looking at it like this, with the actual numbers in the boxes, is just a nice way to kind of understand where the risk lies. Is it more related to the severity? Is it more related to the probability of occurrence? And are there a lot of failure modes that show up in the orange and red, or are the majority of them in the green? Right. So just kind of a traditional way to show it, which has quite a bit of value. All right. So now I'm going to ask you guys to do a class exercise, and what I'd like you to do is I'm going to present the exercise, and then I'm going to wait a few seconds, and at that point I'd like you to pause it and actually do the exercise. And then once you're done working out the exercise, continue. So I'm not going to leave more than a few seconds gap, given that this is a recording. Okay. So given the following information, at what level would the failure mode risk have to be accepted at? And one thing I realized is missing from this slide is where the customer, program manager, and chief engineer accept risks at. So essentially what I'm actually really looking for in this particular problem is for you to determine what the severity and likelihood is of the particular failure mode, given what I'm going to say next, okay? So a system failure mode would cause identifiably critical damage to the system and extensive repairs to resolve the effects, and therefore at a critical severity level, all right? So I've given you essentially one of the two answers. And then the next one is the failure mode failure rate is 0.5 failures per million hours, and the mission duration is a continuous operation for 10,000 hours. Remember that in this particular case, we're using the exponential distribution. So now, again, determine based on those pieces of information what the actual risk of that failure mode is. And this is a good time to pause it. Okay, we'll continue on now with the answer. So again, using the exponential distribution for the reliability, lambda is 0.5 times 10 to the negative 6. That's times 10 to the negative 6 because it's per million hours. And then the time value is 10,000 hours, right? So if we plug that in, we get a probability of 0.005. We can go to this table over here on the right side and see that we can actually use this to determine where the probability of occurrence fits. And 0.005 fits right in the D category between these two values right here. Okay, so knowing that and knowing that I gave you the severity of being critical, the actual risk of this failure mode is 2D, which is moderate, right? So it's in the yellow area. So you can see that right here. So this is the step that you would take with each failure mode. And in this case, we have the actual failure rate, which is nice. We have the time value. Those are some things that we need to have in order to determine that risk. But sometimes we don't have that information. So sometimes the actual assessment gets a little bit more uncertain. And that's why we have things like the definitions that go with this table, which I showed a few slides back. And we can use words like remote or occasional to better fine-tune our estimate of the likelihood if we don't have the data, right? And I will say it's standard practice when there is some uncertainty in either in the failure rate or in the knowledge of how often a failure occurs in the lack of data, to fall kind of more on the extreme side of the estimation. So if, let's say there's a few different sources and one says the failure rate is 0.5 failures per million hours, and another one says 0.3 failures per million hours, and then another says it's 2 failures per million hours. It's standard practice to go with the 2 value. I will say personally, I don't know that I agree with that. I think that reliability has a tendency to very often fall on the extreme side and make things look worse than they really are. But that said, that's kind of the standard way that it's done. And unless you have a better idea of the value, it can be hard to argue that you shouldn't use the 2. So just an FYI. So another way to think about the criticality is something that I'm showing here. This image along the bottom was pulled directly out of Mill Standard 1629A. And it essentially says that you can use a formal criticality calculation in lieu of the probability of occurrence. So what you're seeing here is that the vertical axis actually has 2 different scales, and they're the same thing presented differently. So the first one on the inside is the probability of occurrence level, and that's the A through E that I've presented several slides back, right? But it is actually possible to think about the probability of occurrence as a criticality number, which is a little bit more of a refined number. And let me explain to you what that means. So again, also pulled directly out of Mill Standard 1629A is how to quantify the criticality. And it's done using this equation in the middle of the screen, this one right here. The C sub m equals beta times alpha times lambda times the time value, okay? And you'll notice that lambda times t is the same format that you would get out of the exponential portion of the exponential distribution, right? So that kind of looks familiar. And what the addition is beyond that are 2 different proportionate values, okay? So the first one is the conditional probability of emission loss, the beta. And over here on the right side, you'll see the table for determining beta. And so you can have a value of 1, which is an actual loss, a value between 0.1 and 1, which is a probable loss, and then a value between 0 and 0.1, which is a possible loss, and then a value of 0, which means that there's actually no effect. And then for alpha, this is the ratio of the failure mode. So given a failure, or let's say given a component, let's say, for example, there are 3 different failure modes for that component. And by the way, this can be looked up in FMD 97 as well, and it'll give you these ratios. But let's say there's a component with 3 different failure modes. One of them occurs 80% of the time, one of them occurs 15% of the time, and one of them occurs 5% of the time, okay? The alpha values for those 3 failure modes will be 0.8, 0.15, and 0.05. So combined together, they'll equal 1. And this is just a way to express, given that the component fails, it's going to fail into one of these 3 failure modes, okay? And so as a result of that, you can probably understand that C sub m is the criticality number for the failure mode, not for the component. That's what it says right here, right? If you actually want the criticality number for a particular component, you would sum up all of the different CMs for that component. Okay, and then again, the last two are beyond the beta and the alpha value are lambda, which is the parts failure rate, and the T value. Okay, so now the final step of this process, which I'll present today, is the report and the database aspect of it. So at the end of actually quantifying all the reliability elements and filling out the worksheets and doing all the previous steps, of course, it's important to put it together in an actual report that others can view and survey. So the reliability engineer is responsible for actually putting this report together and presenting it to the program for review and for being impounded in some way. Okay, before I go on to the examples here in a second, I want to point out that MIL Standard 1629 in section 4.4.2 also discusses the process. And the process that I just presented was derived from MIL Standard 1629. But I just wanted to point out directly in here that this section actually discusses the steps of the process as well. So come here, check these out as well. Okay, but now I'm going to go ahead and talk about a couple of examples. So I'll run through these. The first one is kind of a space systems example. This is the inertial upper stage vehicle, and it consists of two expandable stages that are deployed in space by either the Space Shuttle system orbiter or the Titan IV launch vehicle. And this is a real example, by the way, so add some good relevance. The vehicle's stage 1 and 2 structures have the following functions and components in common. They have solid rocket propulsion, reaction control, guidance and navigation, telemetry, tracking and command, instrumentation, data management, onboard computer programs, and electrical power and distribution. So one of the keys there is that they're very, very complex, right? So the overall FMEA for this is extremely large, right? The mission is the IUS mission is to place a space vehicle in a desired position within space. The image on the top right shows the particular portion of the system that I'll talk about next. Excuse me, you can see right up here, there's an interface connector in here. It's obviously hard to see, it's a pretty small image, but that's a portion of the system that I'll go into a little more detail on. Since this is a real scenario, I'll point out that it's a hardware FMECA that was actually done for the system. And that relates back to the first portion of this lecture where we talked about the different kinds of FMECAs that could be done. One of the failure modes, one of the many that was actually quantified in this particular analysis was the IUS Stage 1 to IUS Stage 2 interface connector has a failure to separate, right? So and this is actually interesting because it's not one of your traditional failure modes that you would typically find in an FMD style document. This is more that functional approach, right? Looking at what's the function of the connector and just saying it doesn't happen, right? And the effects of that failure are damage to the IUS and or inability for the space vehicle to reach the desired orbit, right? So it essentially increases the drag. It's important to note that this is actually and was noted as a single point failure, so there's no redundancy to it, and it had a category 1 of catastrophic for the severity. So remembering back to the several slides back where we looked at the fever chart, again, catastrophic relates to either moderate, high, or serious risk. Let me make sure I said those terms correctly. It relates to moderate, serious, or high risk. So again, it's in this category right here on the far right side. And in fact, it was extremely unlikely. So it's this 1E, it's this moderate risk category. The possible failure mechanisms and causes of this particular failure mode were poor quality connectors used, which happens all the time. Connectors fail a lot. Obstruction preventing separation, and poor workmanship during assembly, which again is actually something that happens a lot and results a lot of times. The assembly process can result in also bent pins. So if you guys are familiar with that, it's the idea of when you connect to a male and female side of a connector, if it's not done right, it can often bend a pin. And signals which are critical can be sent to other pins which essentially should not have those signals. In this particular case, though, this failure mode would not be detectable, so it had zero detection. Now, in this case, they were actually doing this via a FMECA, so they noted no detection method, but that did not play into the risk, right? Because the risk was catastrophic and extremely unlikely, so the risk was 1E, which is moderate. Given that this would be done with a FMEA style analysis, the RPN would have actually had probably a value of 10 for the probability of detection, which would have actually driven the risk up. So it's kind of important to note those differences in the two styles of analysis, because in this particular case, it was a disadvantage to do it with a FMECA style analysis. As I've already mentioned, it had a likelihood value of E, which is extremely unlikely, and catastrophic severity, so it results in a moderate level of risk. They noted the compensating provisions and corrective actions, which are, in this particular case, there's just one, which is to document this in the critical items list, meaning document the connector, the actual component in the critical items list. And when it goes in the critical items list, it gets managed separately and has a higher level of scrutiny. But it doesn't actually do anything to the design. So, for example, another corrective action, in hindsight, of course, would have been to add a detection method. Even if it was somewhat rudimentary, it could have provided value. Now, given that it was detectable during the mission, maybe there's nothing they could have done about it, and maybe that's why they didn't take that step. But that could have been another example of a corrective action. Okay, what actually happened in this particular case, so the FMECA was done during the design process, of course. Later, the IUS Vehicle 21 had a failure. It was on April 9th of 1999. There's a reference here to provide some more information if you're interested in the failure or the particular case that occurred. But essentially, the failure observed was the inability for DSP satellite space vehicle to reach desired orbit because IUS stage 1 and 2 interface connector failed to separate. So it was the exact failure that was observed in the analysis, and even the effect was essentially right on, which is, I guess, encouraging from an analysis standpoint. But the disadvantage, of course, is that, the mission couldn't be executed, so there was some value in why they were actually trying to place that system in a particular point in space. And then also there's the obvious loss of the value of the satellite, which was $180 million. So kind of a big loss financially, and this is also $180 million 18 years ago, so quite a bit larger even today. The root cause on a post-examination was that the engineering assembly drawings were inadequate, and there was improper application of thermal tape at connector separation plane. So it's interesting because if you think about the way that this took place, the assembly drawings are something that are very common in design. Every system has a pair of assembly drawings. And it's interesting to, as a reliability engineer, to think about the fact that something so simple as an assembly drawing could be the primary root cause in such an important failure. And thinking about this, and I've seen this over and over and over in practice, from assembly drawings to other procedures. And it's important to understand that even the simplest things that we kind of assume are correct because we do them so often are often the things that are not well done. And so I guess the takeaway is that don't assume that things that are common are going to be well done, because that would be a very big mistake. Okay, that's example number 1. I'll move on to example number 2, and this is actually something that you guys saw in a previous term, so you guys have been a little bit familiarized with this example. The example is of a fail-safe gate valve, a hydraulically actuated fail-safe valve. So the image up here in the top right shows the valve and all the different components. The working fluid or pressure is, the fluid essentially flows through this canal here. There is a stopper in the way, and in this particular example here, it's shown as being closed, and the hydraulic piston here, which, the hydraulic piston here can move in order to open this, and at a relaxed position, the spring pushes the piston back to the position where it's closed. So hydraulic moves it one way, spring moves it the other. So take a second to think about what the function of this particular valve is, and some of the different failure modes and their associated causes. So again, this would be a good point to stop the recording. I would say think of the function, and then think of about 5 different failure modes and their associated effects. Okay, so again, go ahead and pause. I'm going to wait just a second, and then I'll go ahead and keep going. Okay, so first off, the essential function of the gate valve is to control the flow of fluid in a pipe. The table in the middle of this slide shows a variety of different failure modes and their effects. And so I'll give a few examples. So let's say the failure mode fails, or the gate valve fails closed. The effect of that is flow cannot be stopped. Fails open, there's essentially no flow, right? If the failure mode does not open fully, then there's of course a reduced amount of flow, or it could be does not fully close, which would mean there's some flow when there shouldn't be. Does not respond to the controller, there's a loss of control over the flow, and that actually the does not respond to controller kind of plays into some of the other ones, because the loss in control may result then in a situation where there is a failed open or a failed closed, which then leads to the effects on the top right. So there's a little bit of kind of propagation of failure depending on how you look at this. And then there's failure modes, leaks through or leaks around valves, which would result in a loss of fluid, and a potential hazard as well, because it obviously doesn't show in this case what the fluid is. If it's something like water, it's obviously not such a big deal. But if it's some sort of oil or even something, some sort of acid, depending on what sort of facility is operating, then of course there could be the hazard as well. And it's important to know that when quantifying the failures later on, that, for example, the type of fluid will result in the severity of that failure mode. And so you can imagine a situation where this exact valve is used in different places around the system, and it would not be true that you could just take an analysis from one portion of the system for this component and copy and paste it to another portion if the working fluid is different. Because again, the severity will change. It may be true that the probability of these failure modes is the same, but the severity of those would be different. Okay, so that example was just to point out and just to go through the example of finding the failure modes and looking at their effects. This final example is a little bit more detailed in terms of the system, and this is for a space shuttle main engine. I will go through, I've got several slides on this. I'll go through a portion of those slides because they do get quite detailed and maybe a little bit overly detailed in certain areas. But I'll show you all the slides, and you can go through each of them in more detail if you would like. But just to set the stage, there is a little bit of terminology that goes with the example. The MOV is the main oxidizer valve. The MFV is the main fluid valve. MR is propellant mixture ratio. LOX, liquid oxygen. MCC, main combustion chamber. And ASI is the augmented spark igniter. And so you'll see some of these used on the next couple of slides. So first of all, the SSME, or the Space Shuttle main engine, has a variety of different components that it interacts with, including the space shuttle, the propulsion system, the fluid tank, and the guidance system. And in just a minute, I'll show an example of what this actually looks like. Part of this activity, which I pulled from other sources, was, of course, to do the reliability prediction, which plays into the FMECA. And so it's noted here that the reliability prediction for this particular system is a really large task. And part of that is because the importance of the system, when something goes into space, of course, it's a lot more expensive, to be honest. And so the certainty of the analysis has to be that much better, as we could kind of see in the first example I presented, where $180 million was lost. So the amount of analysis that goes into a space system relative to some of the more traditional type of DoD systems is very heavy. And the other thing that plays into the amount of effort that goes into analysis is whether it's a manned system or an unmanned system. So for example, weapon systems like missiles and torpedoes typically don't require as much analysis effort as an automotive system. And that's just because people are not involved. Now, there are certain portions of the mission timeline where there are people involved. Of course, during manufacturing, during transportation, during launch, and there are sometimes people involved. But again, the systems themselves are supposed to be dead during that time, and so all the way up until launch. And so the level of analysis effort is a little bit less for those types of systems, whereas an automotive vehicle, the scrutiny does go up quite a bit. And that would be the same for those of you guys who are doing the submarine. So the SSME includes a variety of different subsystems. It has low and high pressure hydrogen and oxygen turbo pumps. It has main fuel injectors and main combustion chamber and a nozzle. And again, I'll show an example here in just a second. The thermal stress due to the temperatures are pretty impressive on this thing. So it goes temperature-wise, its mission ranges from negative 423 degrees all the way up to 6,000 degrees Fahrenheit. This is something that not many systems see. And if you think about reliability and really the root of it, it's driven by its environment, right? So if the environment is stable, then there's not typically a whole lot of interesting stuff to analyze unless it's a really extreme environment. But the change in environment and also extreme environments themselves are really what drive most of the issues in the system. And so this particular system has a huge range in its requirements for temperature. And it also has very high performance requirements for the RPMs of the turbo pump, which is 30,000, and the pressure of 6,900 psi. So it's a pretty extreme environment that this thing is operating in, and it's very high, very critical type of performance as well. So that includes, or that adds to the challenge. In this example, in this rocket engine, stored fuel and stored oxidizer are pumped into the combustion chamber where they get mixed and burned. And you'll see this in just a second in a figure. The combustion chamber produces large amounts of exhaust gas at high temperature and pressure. The hot exhaust is passed through a nozzle, which accelerates the flow, and then thrust is produced. So this is kind of the high level, 10,000 foot level of how the system actually functions. Here's an image of it. You can see the fuel tank and the oxidizer tank, which of course down here come together in the combustion chamber and are pushed out the backside. And if you're interested in the math behind it, the thrust is produced by this equation here, right, which includes the pressure, the mass flow rate, and the velocity. This kind of traditional type of mechanical engineering stuff. Okay, so here's a little bit more on how it works. I'm not going to go through this slide, but I'll show it. And then there's also just, again, some more details on this slide as well. And also a little bit more details on this side. So I'm going to go ahead and skip over these guys, but if you're interested, read through those in more detail. This is a more detailed schematic of the engine. It provides a little bit more detail so you can kind of see it at a higher level of fidelity than I showed on the other slide. And then another slightly more detailed of the actual turbo pump as well, just so you have a visual for kind of what this looks like. Okay, now getting to the actual FMECA that was done. I'm only showing in this particular case just 5 different failure modes, but I wanted to show essentially a more complete example of a FMECA. And so from a worksheet standpoint, right, because what I showed in the previous examples was just portions of that. And so this shows more of a complete example. And so as an example, you can look across the top row, which shows the column headers. There's the mode number, so there's uniquely identified, the failure mode, detection method, effect description, and the effect on the engine. Okay, so one note about the mode number on the far left, you can see that it's labeled 1 through 5, so this is essentially just showing that there are 5 different things being analyzed. Whether they're the same component or different components doesn't really matter. They're just different lines in the FMECA. One note about that though, I don't particularly like the way they've done it here, and I think it could be better. And so the note I'll make about that is that one of the most effective ways I've seen this done is to list the mode number by the subsystem that it's in, and then by a number. So essentially what I think they're missing here is a subsystem. And that's important because when you think about how many lines there will be at the end of the day in the FMECA, it could be thousands, many thousands. If you're interested in searching on that, which you will be at some point, you want to set your FMECA up in some way that you can actually make it searchable. And I would suggest having at least a column, so you can do them in the same column or you can do them in separate columns. I would suggest having a couple of columns to be able to filter the data. So the mode number would essentially become a few different columns. You could have the first column be the subsystem. Depending on how big your system is and how many levels of hierarchy, you may have a secondary, more of a subsystem level or even a component level category next. And so in this case, the first column might be, because this is of course part of a bigger system, the first column might be SSME for these 5 failure modes. The second column might be turbopump, right? So we can then filter our results on SSME and the turbopump later on if we just want to look at that portion of the system. And then the final column would be then just the number that they show here. And this is, by the way, very important for review purposes. So as we mentioned in the process earlier, there's a variety of different people that will get involved in the FMECA process. You want to develop your worksheets in a way that lends their help best. Meaning that if you have an SSME SME, or maybe it's a turbopump SME, you want to be able to deliver the portion of the worksheet that's relevant to that person with the least amount of effort on your end. So not to belabor the point too much, but it's really important to have some way to be able to filter, and the mode number is a really good way to do that. Okay, the second column is the failure mode. Those are pretty straightforward, right? So internal leak or premature opening, failed closed, things like that, right? The next column is a detection method. So for example, in the first failure mode of internal leak or premature opening, the detection method is CC injector pressure and temperature monitors. So those would monitor somehow if there was some sort of leak, or MOV DS skin temp, or MOV position monitor. The effect description, accumulation of oxidizer in main combustion chamber prior to start signal, or possible hard start. And the effect on the engine is hard start or may damage engine, which is a little bit vague. Okay, and so you can kind of see the style of this worksheet. This next page is going to continue on, so I'll continue to talk about mode 1, which is shown here, right? So this is a continuation. So we had the effect on the engine, and now the effect on the mission or the vehicle, which in this case is a possible launch delay. Now in this example, the criticality is shown as 3. It doesn't show the severity, and it also doesn't show the calculation behind the criticality, but we covered that earlier, so we can assume that they use that methodology. The possible causes are contamination on seat, damaged seat seal, and premature open signal. And then the preventative action is leak and functional check during pre-launch preparations and pre-launch purges and controller. And so the preventative actions in this particular case are important because this is one of the things where you can mitigate a lot of failure modes by checking them right before use. So any of the storage, any of the transportation type of failure modes that can occur in systems can often be eliminated. The probability of them occurring can be eliminated primarily by checking them right before they're used. Right? So if you can imagine, again, a missile that's sat in a silo for 10 years and is then going to be launched, a lot of the probability of occurrence of that failure mode will be due to that 10-year period where it's sitting through these diurnal temperature, humidity, pressure, vibration cycles. And if that particular failure mode in some form or fashion can be checked on right before launch, it can actually eliminate a lot of the risk. So that's good to note. The other thing I'll mention about this example, this is maybe a slightly odd thing to point out, but if I were doing this example, I would probably organize the FMECA a little differently. I don't know that I would have the causes toward the end. I think that that's a little bit out of order. Now, it may not really matter one way or the other for the most part, but I will say, though, that one of the important steps in the FMECA process is the review by the program and by individuals on the program. And it's important to set up the FMECA in a way that is logical to those people so that they can review it the most effectively. If it doesn't make sense, the value that you get out of their review will certainly be reduced. And that's something that, of course, you'd want to avoid. Okay, so the example that I've shown here is certainly one very small element of what was a very, very large FMECA. And so just kind of pointing out here that there is a lot more that goes into this. Okay, and that concludes the FMECA lecture. So there are a couple of conclusions here. A qualitative reasoning approach best suited for electrical and mechanical types of systems. Actually, that certainly is true, and that's the most traditional way that they're used. But it is also true that FMEAs and FMECAs are good for software-based systems, cyber-physical systems. So they're quite broadly used. And in fact, I'm going to update this statement to be more broad than just hardware and electrical systems. It really is good for all systems. These assessments consider how the failure modes of each system component can result in performance-related issues. And depending on how the analysis is, also potentially safety issues, but that's technically falls in a different risk-based analysis. And then it also ensures that the proper safeguards are put into the system so that it works when it's supposed to. Okay, thank you guys.